Hi all, my name is Karthik Vaidyanathan. I'm a computer science PhD student at Gran Sasso Science Institute in Italy. In this presentation, I would like to talk about a paper titled Leveraging Machine Learning Techniques for Architecting Self-Adaptive IoT Systems. This was done in collaboration with my supervisor, Professor Henry Muccini from University of L'Aquila. We live in a world of Internet of Things, where we have IoT devices being used in different walks of life. Hence, architecting these systems in the proper way is of utmost importance. The figure shows the standard set of components in an IoT architecture. There are devices which can be sensors or actuators which communicate or receive data to or from the cloud through the gateways. The cloud in turn will process the data using different algorithms and derives various analytics from these data. Further, they are sent to mobile apps where they are visualized. Now, even though this looks pretty straightforward, there are a number of challenges that exist in architecting any IoT system. These challenges relate to the heterogeneity due to the different types of components in an IoT ecosystem. Assuring quality of service is hard as different issues related to response time, packet loss, energy consumption, etc. needs to be handled. Different devices with different communication standards and protocol leads to the problem of interoperability, and the list goes on. A recent article from Cisco states that around 75% of the self-initiated IoT projects were failures due to the lack of proper software engineering practices. All this particularly have a big impact on the overall quality of service. Two such important quality of service challenges in IoT, which we focus in this paper, are related to energy consumption and data traffic. Devices might run out of battery due to resource constraints. IoT devices are expected to consume around 21% of world's electricity in the near future. The amount of traffic generated can also impact the overall performance, and this has a big impact as well on the global carbon footprint. And this is shown as per the latest studies. So ensuring energy efficient systems with optimized data usage is of utmost importance. Now, let's put this in perspective. Let us consider a real scenario. So NDR, which stands for Notte di Ricercatore, is a street science event held at the city of L'Aquila as a part of the European Researchers' Night. It is a one-day event where public and researchers are brought together to share different types of infotainments from morning to late night. The image on the left shows the overall event map of NDR, and the image on the right shows the screenshot of the mobile app, which can be used by the public to locate different events in the city. So we have collected some observations from the past editions of the event. One, around 25,000 people attend the event. Late hours are usually more crowded than early hours. Weather condition affects user preferences. And then crowding happens in the city center. This is because of the less availability of parking lots, and people usually don't know which venues are full and which are available. So this leads to crowding. Further, we also have some constraints in this case. One is the limited availability of external power source, as the event happens in the city center and the number of power sockets are limited. One of the way by which you can reduce the energy consumption of the devices, so to save power, is to reduce the communication. However, less traffic in the network can affect the service accuracy, and too traffic can lead to congestion. So the figure here shows the high-level architecture of a part of the system that we have planned for NDR. It consists of two main services. One is an automated parking lot control, which uses parking mat sensors in the entrance as well as in the exits of the parking lots. These are then sent to the display units in the parking lots as well as to the mobile devices for notifications to the user. Another is the service of automated venue control, which uses a set of handheld RFID readers and people counters at the entrances and exits of every venues. And this allows to monitor the crowd movement and to provide real-time updates. With these two in place, the crowds can easily be redirected to different venues and parking lots. Then the question is, what about the constraints? How can the uncertainties of power issues and data traffic be handled? One solution is to use self-adaptation mechanism where the system can adapt based on changing context so as to guarantee the quality of service. The image here shows the famous Mepke loop of self-adaptation. In general, if you consider the types of self-adaptation, it can be done in two ways. One is reactive, where the adaptation is performed when a need arises. Although this is good, it is not effective as violation has already happened. The other one is to use proactive technique, where the need for adaptation is predicted and the best action is taken. In either case, simple reconfiguration methods cannot be used, as we have already seen, reducing the energy reducing the communication to save energy or doing vice versa may not be optimal. Hence, we need to go for structural adaptation techniques. So towards this, 3 different patterns for self-adaptation in IoT or CPS in general was proposed by Musil et al. So each pattern has their own advantages as well as disadvantages. Intuitively, this can be thought of as edge, fog, and cloud. So SU in the figure, or synthesize utilize, is a completely decentralized pattern like that of an edge where the sensors have the ability to decide. SC or synthesize command is more like a centralized pattern, and it is like a typical cloud-based system where the sensors send their data to a central processing unit, which then performs the decision making. CO is a decentralized or a semi-decentralized pattern, which is similar to fog, where the sensors send the data to a controller component, which further performs the decision making and forwards the data to a central storage. Then the question can be, why not use one of them to achieve the goal? Well, there lies the problem. So the plots here shows the energy and data traffic consumed by the system during 1 hour simulation of the NDR architecture. So we have done the simulation using each of the 3 patterns. As we can see here, CO, which works best for energy consumption, here works the best when it comes, works the worst when it comes to the data traffic. This is because CO, being a semi-decentralized pattern, has an additional controller component in between. Hence, the total energy consumed by the sensors will be less, whereas the data traffic in the system will be high. Similar is the case with other patterns. So those that work well in the case of energy might not work well in the case of data traffic. Hence, the best way is to combine their use based on context such that we get optimal energy and data traffic in the system. So we know from literature that a proactive adaptation mechanism works better. So the figure shows the flow of a proactive adaptation mechanism where the system continuously collects the data, analyzes the data, makes prediction for any possible quality of service deviations, sees if there are any possible violations. If yes, it identifies an adaptation plan, which is to select the best adaptation pattern, and then it executes the adaptation. So however, although this looks good, one of the problem is that there is no learning. What I mean is that every time an issue happens, the same process is repeated to obtain an adaptation pattern. And there is no way to see how effective was the use of a previous pattern or the pattern that was used in the previous step. So the question is, how can we ensure that the system is able to continuously learn to select the best pattern in any given scenario? Towards this, in this work, we propose a solution which uses a combination of deep neural networks and reinforcement learning techniques. So what happens is that once a possible violation is identified, our approach checks if it is the first execution of the approach. If yes, it identifies a suitable adaptation plan by selecting the best pattern and it is executed. If no, it obtains the feedback of the previous pattern selected, learns from it, and then executes the adaptation. So this happens continuously and the system keeps improving with every adaptation performed. The figure here shows the overall view of our approach. As you can see, it is based on the MAPE loop of self-adaptation. Consists of the managed system and a managing system. The managed system basically represents the running system, which is based on an architecture and a set of quality of service requirements. The data obtained during the execution are stored in a data store component. Managing system, on the other hand, consists of machine learning engine and an adaptation executor, which are responsible for analyzing the data and performing the adaptations by selecting the best adaptation pattern. The architecture is designed such that it supports dynamic pattern switch in runtime to enable adaptations. Now, let us look at one by one. So first part is, once we have the architecture, is to define the quality of service requirement. So quality of service requirements are basically defined by using 4 thresholds. One is HE, the maximum energy that can be consumed for a given interval. Then LE, which is the energy consumption below which maximum energy is saved. Then we have HD, which is the maximum number of messages that can be sent in a given time interval. Above this might lead to congestion. LD is the minimum traffic required to maintain service accuracy. So this can be defined by the stakeholders. Then we have the data store. So data store basically stores the system execution logs. In the context of NDR, these logs contain energy consumed by sensor components as well as the message sent for different intervals of time. These intervals may not be uniform. Now comes the main thing, which is the machine learning engine. So the machine learning engine basically works in 2 phases. One is a build phase, where it uses the data obtained, which is the data of the data traffic and the energy consumption, to create prediction models using deep neural networks, particularly long short-term memory networks. This phase is executed periodically so as to keep improving the machine learning models. Next is the operational phase, which is the real-time phase, where the real-time quality of service data of the IoT system is continuously monitored to make predictions using the trained models, and based on this, the pattern is selected by the decision maker, which uses Q-learning to select the best adaptation pattern. Now, going inside each of the components in machine learning engine, the first important component is the feature extractor. So feature extractor basically takes the raw data from the data store, converts it into a time series data set. So one of the important quality of, or the aspect of quality of service data, is that they have a temporal nature, and this can be exploited to convert the problem of predicting the expected course into a time series forecasting problem. The energy consumption data is converted into a multivariate time series data, as the energy consumption of each sensor component also depends on the communication with other sensors. The data traffic is converted as a univariate data set, as it is a total data traffic in the system. So in the case of data traffic, as I said, it's more at the level of the system, so it's considered as a univariate data set. These features are then normalized, and the data is split into training set and testing set. The training set is sent to the LSTM component, and the testing set is sent to the model evaluator. As I said earlier, we use LSTMs for building the forecast models. So LSTMs, as some of you might know, belongs to the class of recurrent neural network, and it has been shown to be very effective in sequence prediction problems related to speech recognition, language processing, time series forecasting, and etc. So for each of the quality of service attribute, this component creates a trained model using the training set for a defined prediction horizon H. The model evaluator then checks the accuracy of each such models. We had already shown in our previous work why LSTM works better than other state-of-the-art approaches, and hence I'm not going into the details of it here. Now, once we have the trained model, the next thing is that the trained model forms the quality of service predictor for the operational phase. So it continuously obtains the quality of service data, and then this is further sent to the decision maker. So the decision maker uses Q-learning for selecting the best adaptation pattern. The main reason for selecting Q-learning is that it is a model-free technique. So it does not require any trained model, but the training, or rather the learning, happens on the fly. So coming to that, the image shows the kind of a common well-known diagrams of a Q-learning process. So there will be an agent which interacts with the environment by performing an action. And based on the action performed, it gets some reward, and it changes from one state to another. This is the most commonly used techniques in robotics to train robots to follow different routes and paths. So applying the same principle to the adaptation process, we can consider the architecture like a robot in a grid. And imagine that it has to go through the grid as shown here. The goal will be to reach the state G, which can guarantee minimum energy consumption with the required data traffic. Hence, at every point, the architecture needs to select a pattern such that the system will eventually reach this goal state. So keeping this principle in mind, we first define the states. So state space basically represents the combination of possible quality of service states and patterns. Now the question is how to determine this quality of service state. So every time the quality of service forecasts are produced for energy and data traffic, they can be categorized into one of the threshold classes. So if the forecasted energy is above HE, then we can say that the state is HE. Similarly, we can do for traffic as well. Then we can obtain states like this. So when we mean HE LD underscore P1, it means that the forecasted energy is in the threshold of HE, then it is below LD, and the system is currently using pattern 1. Like that, we can form the state space. Now, action space, on the other hand, represents the switch to different patterns. Rewards are basically the mapping of each state to an integer value. Means for reaching every state, an integer value is assigned as a reward. Now, Q table forms the heart of Q learning. It is an n by m matrix where n represents the total number of states and m represents the total number of actions. Each value inside the Q table is a state action pair. It denotes the relevance of taking an action A from a state S. So the image here shows the overall algorithm of the decision maker. I'm not going into the details, but I just want to highlight some of the key parts of the algorithm. So the first part, as I explained earlier, is that Once we get the quality of service forecast, we identify the state, and based on this, an action is selected. Now, the action is selected by identifying for which action the value of Q of S comma A is maximum. This can be obtained from the Q table. So then the Q table is obtained using this, the Q table is updated using this formula. The action is then sent as the decision to the adaptation executor for executing the adaptation. One thing to note here is that the entire process happens in a proactive manner. So for every decision made, the forecast in the next time step is implicitly used as the reward or penalty for the decision. This way, the system keeps learning continuously from every adaptation. Now, the question is, how can this be implemented concretely? So we used NDR case for implementation. We use a simulated version of NDR. For the simulation purpose, we use the tool CupCarbon. And we also modified the source of CupCarbon to support dynamic architectural adaptation. So to implement this whole approach, we used a layered architectural approach with some big data stack, as you can see here. The forecast models were developed using Keras. Kafka was used to stream the real-time energy consumption logs as well as the data traffic logs from CupCarbon to Spark, which was used in streaming context. So Spark then uses the models to make predictions, and this is sent to decision maker, which uses the Q-learning, and this was implemented using native Python. And then we have a adaptation manager component, which is basically a Java-based component, as CupCarbon is implemented in Java, and this manages the pattern switch. For storage and visualization, we used Elasticsearch and Kibana. The tool is also available in the link below. Now, the important part is to see how good is the approach. So for this, we evaluated the approach on the basis of effectiveness and efficiency. Effectiveness was evaluated in terms of forecast accuracy and stability, energy and data traffic consumed by our approach, and the adaptation quality. Efficiency was evaluated based on the number of adaptations performed and the time taken to perform the adaptations. Now, coming to the experiment and data setup. For deploying the system and running the experiments, we used a high-performance computing cluster with 4 compute nodes, where we deployed the Kafka, Spark, and Elasticsearch Kibana stack. The CupCarbon simulator was run using a desktop machine. The thresholds were decided based on the experience and experiments. A forecast horizon of 10 minutes was selected, and this was selected after determining what gives the best window for performing the whole proactive adaptation process. We first simulated the system for a period of 10 days, during which we randomly vary the pattern. This was done to capture the variations that might happen during the runtime. And this formed our basic training set. Then we created 3 data sets by running the simulation for each of the pattern, and this was done for a period of 3 days. And this formed our validation data set. Finally, the real-time experiment was run, which was done for a period of 24 hours, as NDR is basically a one-day event. And this complete simulation was done based on the real values observed from the case study. So the first question is, how accurate and stable are the forecasts? So the graph shows the plot of real versus forecasted values. We can see that the forecasted graph is able to follow the actual values. In both cases, we computed the normalized root mean square error between the actual values and forecasted values, and this was found to be very minimal. We also tested these models across different validation data set, as I explained earlier, and the NRMSE was found to remain stable. So these models were further used for real-time phase. So then the question is, how much energy and data traffic is saved by this approach as compared to the individual patterns? So for measuring this, the energy and data traffic consumed by each of the pattern as well as our approaches were calculated for a period of 24 hours. The figure here shows the bar graph of the normalized energy and data traffic consumed by each of the approaches. CO, as expected, being semi-decentralized, consumes the most amount of data traffic, but as it is semi-decentralized, the energy consumed by the sensors is low. Reverse is the case with SU, where the energy is consumed is very high due to the completely decentralized approach, and the sensors end up performing most of the computation. On the other hand, they have less data traffic as the communication with the central storage is less. SC, on the other hand, being fully centralized, consumes energy more than CU and less than SU. The data traffic is higher than SU due to its centralized nature. Now, coming to our approach, we can see that it is able to provide energy efficiency at the same time maintaining the required data traffic. Additionally, the table shows that the energy consumed by each approach along with the data traffic for a period of 24 hours. The last three columns shows the violation of data traffic and energy thresholds. So we can see that the violations while using our approaches are the least as opposed to the others. Now the next important question is, what about the adaptation quality? How much does it improve with time? So to calculate the quality of adaptation performed, we computed how the energy and data traffic savings improves as time progresses. To do this, we created a cumulative plot of the energy consumption and data traffic while using each of the approaches aggregated over a period of 4 hours. So basically, we will have 6 interval periods. These plots are depicted here. As we can see, in the case of RL, the energy consumed is not growing at a higher pace as opposed to the other patterns. The growth is per se even less than CO, and this shows that as time interval goes on, more energy is being saved as compared to the previous interval. The same holds for data traffic as well. We can see initially SC is better than RL, but towards the end, RL is able to save more data traffic than SC. So overall, we can see that the approach is effective in terms of accuracy, energy consumption, and data traffic. Also, we saw that the quality of adaptation performed improves with time. Now, the next thing is efficiency. So to compute the efficiency, we first computed the total number of adaptations performed by our approach for every 4 hours. And we found that on average, the number of adaptations performed is only 13. And the total number of adaptations performed for the whole 24-hour period is 79. So every 4 hours, 13 adaptation means that out of 240 adaptation intervals, only 13 adaptations were performed. This was because the approach is able to learn efficiently from every adaptation performed, thereby minimizing the number of adaptations. Next, we computed the time taken to perform each adaptation. On average, the entire approach took around 0.23 seconds for performing the whole process of adaptation. This means the process starting from prediction to selection to execution. In this, the major time was consumed by adaptation manager for the over the network communication of the patterns. So concluding, we saw how our approach can produce accurate quality of service forecast, how the combination of machine learning techniques can produce better quality of service guarantees. We also saw how we can move from traditional self-adaptation to self-learning, where we can have learning enabled through adaptations. So some of our ongoing and future work include, but not limited to, integration with quantitative verification techniques. So the first part was presented in ICSA 2020, then extension to more different types of quality of service parameters and more fine-grained topologies. We also plan to include fail-safe mechanisms in case of scenarios where something happens which we had not predicted. So that's all. I hope you enjoyed the talk. In case of any queries, feel free to contact me. Thank you.